right, what is up, everyone? We are live. I feel like it's been a little while. I think we missed last week, so I'm glad to be back here. We're back to our regularly scheduled programming. If you're new around here, what we're going to be doing is I'm going to be going through a recent Leetcode contest, and we're going to be just live solving some of the problems. I'm going to show you my thought process, how I tackle these problems, how I think about a problem that I've never seen before, and how I work towards a solution. Because at the end of the day, when you're preparing for your interviews, that is the thing that you need to be able to do, right? You need to be able to actually go into an interview and answer a problem that you've never seen before. So let's just jump right in here and take a look at some problems. So we'll jump over to Leetcode. Let me get rearranged here a little bit. And as I go through this, if people have questions, anything you're unsure about, feel free to drop those in the chat. Happy to discuss as well. But let's get into, so this is contest 309. I'll put this in the chat as well in case anyone wants to follow along. And let's go ahead and jump into it. All right, so we're given two positive integers, start position and end position. Initially, you're standing at position start position with an infinite number line. With one step, you can move either one step to the left or one step to the right. Given a position integer k, return the different number of ways to reach the end position starting from the start position such that you perform exactly k steps. Okay, since the answer may be very large, return it mod 10 to the 9 plus 7. Two ways are considered different if the order of the steps made is not exactly the same. Okay, so in this case, let's look at an example here. We have our start position is 1, our end position is 2, and k is equal to 3. So if we want to, ultimately we want to move one position to the right, and the question is how many different ways are there to do that? So we could go, in this example, we could go right, right, left. We could go right, left. We go right, left, right, and we could go left, right, right. Right, and so those are the three possibilities. And I think this is a good example of one that would be helpful for us to actually draw out, because it's going to be a lot easier to kind of figure out what we're doing if we can visualize this a little more rather than just talk through it sort of conceptually. So let me see if I can get this share going here. All right, so yeah, what we have is we have a number line, something like this, and then essentially what we're saying in this example is we're starting at this point, and our target is this point, and we want to take exactly three, and we want to get there in exactly 3 steps, right? So we could go 1, 2, 3. That was one option. We could go 1, 2, 3. That was another option, and then the third option was we could go 1, 2, 3. Right, and all of these 3 different variations are going to get us to the destination. And so that is how we are. That is how we are getting to this solution. Now the question is, how do we solve this? And I think this is a good example of one of these problems where let's reduce this down to, what is it that we're actually being asked to do really here? What we're really being asked in this problem is we want to find, obviously, again, the number of ways to get from point A to point B, but the question is, like, we know kind of what the net moves are, right? Like in this example, we know that the net movement is 1 in this direction. Right, so essentially, we can pick any combination of moves to the left and the right where we end up with a net of +1, right? Where we end up with one more move to the right than to the left. And so every combination in this has to have 2 moves to the right and 1 move to the left. And any ordering of these combinations is going to give us a valid result, right? Because it doesn't matter what order we go, and it just matters that we do it in order. And so really, with this, what we're asking is, okay, well, how many different combinations are there of this? Right, so in this particular case, we want to basically figure out what are the number of combinations of right moves and left moves that match this. And so we could do this. This isn't, a problem that we could do, for example, recursively. I'm imagining that we might want to try doing some sort of dynamic programming. There's probably something fairly easy that we could do using dynamic programming, where essentially, it's pretty easy. When we look at this, it's basically we're just saying from a given position, what are the number of different combinations with a certain number of steps, right? So we could cache that fairly easily. Now, is there a more efficient approach to doing this? Possibly, right? Like whenever I think about, really this becomes a combination problem, and so my immediate question is, are there any is there a greedy approach to doing this, right? And so the greedy approach, what we could consider, I'm just trying to think if there's any way in which we could even like calculate this directly mathematically, right? Because we know what the for example, we could count just the total number of combinations of right and left moves, and then of those combinations we kind of need to select out the total number of combinations where there's the right ratio of left moves to right moves. I'm not really sure how we would do that, and so my immediate thought is, let's try implementing like a brute force solution here, and then we can use some dynamic programming, right? So to do this, what do we need to do, right? We need to say basically if this should be fairly straightforward, and I'll actually separate this out because it'll make it easier for our it'll make it easier for us to do our dynamic programming. So that's what I'm trying to say. I rather than start an end position, I'm going to actually I'm actually going to track like what is the relative position to my end position. So I don't know that that's really that necessary per se, but this is basically going to be end position minus current position. Right, so if it's basically going to be like, how far are we away from the end position? If relative position is equal to 0, then that means that we are at our end position. And so in k, now if k equals 0, then basically we are going to return, or actually we really need to check if k is equal to 0, if relative position is equal to 0, then that means that we have found a valid path, and so we return 1. Otherwise, we return 0. Now, if we don't, then we have two options, right? We can either move to the left or we can move to the right, and so we are going to return number of ways, relative position plus 1, k minus 1, plus number of ways, relative position minus 1, and k minus 1, right? Because this is basically, we are using one step and we're either going to the left or we're going to the right. And so to call this, we're just going to say return number of ways, end position minus start position, and k. So it should be something like this. Okay, so that got the right result, and then what we should find is that this gives us a time limit. And also we didn't handle the large sizes, right? So this is obviously not going to work for us because this recursion is going to blow up, right? This is going to be basically a exponential time complexity. So let's take the next step, which in this case, what we can do is we can cache these values, right? So we can cache these values by creating some sort of map or array. I think it's probably going to be easier for us to use a map in this case because we don't know our relative position, which is the key, can be negative. And I guess we really need relative position and k, right? So we have sort of this 2D thing of and then we pass that in here. Alright, so this needs to be integer. DP like that. And then all we're going to do, as we usually would do, is we're just going to, in here, before we compute these things, we're going to check whether or not it exists, right? And so rather than, and so this, when I look at this, I'm also thinking that maybe to make this a little bit easier, it would make more sense to use an array of maps. So, or a list of maps or something like that, but I'll leave this way for the moment. So basically what we're gonna do is we're gonna say if contains key relative position and dp.get relative position dot contains key k, then in this case, and actually really we should do the reverse, right? So if not contains key or not this, then we're going to do our recursive, then we're going to make our recursive calls, right? So we're going to call this, we're going to say result equals this, and then dp it's like more annoying with the maps. We can do dp that contains key relative position. Then we'll say dp dot put relative position and new map. Right, so we're basically going to do this, and then we say position, and then all right, this, and then actually this should be here, so we add it to the map. Relative position and the result, or this should be k actually. And then we return dp.get relative position dot get k. Right, we're using maps instead of a 2D array, but functionally it's doing the same thing, right? It's a map of maps. So I probably got something wrong here. This should not be relative position. Oh, this is just dp.get relative position that contains key. All right, and we need to pass our DP in here. New hash map. All right, so that gave us the right result. Now the question is, I mean, this still isn't going to work, I assume, because we're going to get this overflow. Yeah, like we're not handling the 10 to the 9 thing. So with this, we should just to the 9, right? So this, and then so one, for example, what we could do is just the question with these, I think, always becomes like, where do we mod it, right? Where is the place that we need to that we're gonna get the overflow? And so that's probably gonna be here. So what we could do is something like this, and then that's probably sufficient, because that's the only place that we're combining these together. And because we're modding it here, we should always be returning something that's modded. So I think that that should solve our problem with the mods. I think final has to go first. I don't remember. All right, this needs to be cast to an integer, because we are gonna we can still keep using integers here. So line 20. I just like what I've found happens a lot is like we'll add these together, and there's going to be an overflow before, and we probably want to cast these both to longs as well, because you can end up with stuff where it's like we're adding two integers together. Like if we cast this whole thing to a long, right? What I've seen happen is we'll add two integers together, it will overflow, and then we'll be casting it to a long. So we probably need to make sure that both the individual ones are treated as longs first. It always gets kind of weird with these ones that have the really big, like just making sure that you're handling these things in the right spots to avoid those overflows. Okay, so we're still getting a time limit exceeded. On the very last, so it passed all the test cases, but we're getting it, that, let me try this again. I'm not sure. All right, so interesting. That means that we're probably just right on the cusp there of being too slow. Yeah, I mean, we can see that these solutions are going up to 1600 milliseconds, and ours took 2500 this time. So obviously we want to, let's see if we can make this a little bit more efficient here. And so the first thing that I'm thinking is, this is one where using implementing a bottom-up solution is probably going to be a lot faster, because using these maps is super slow. The other thing is that I think that we can probably prune this in a couple interesting ways. So I actually want to go back to this this way I can have it full width. So here are a couple things. One is if the absolute value of relative position is greater than k, then we can never get to k, right? So we could immediately prune a decent part of our tree from that, right? So we could say, this would basically say if math.absolute value of relative position is greater than k, return 0. So that's probably going to save us some time right there. I'm just curious, like, if we let's maybe do this incrementally, because I'm curious how much this will actually make a difference. So in this case, okay, see that alone dramatically improved our time complexity, right? So what I basically did there was I said, okay, well, if we get to a position where we're like so far away from our target position that we can never get there in k steps, then we know that that's always going to be invalid. And so that's a simple way that's a simple optimization that we can make. We could also say if it's exactly equal to k, then there's one way for us to get back. So that's another, small optimization that we could make, which is if this is equal to k, return 1. That, I don't know that that's going to make a significant difference, but it did improve us a little bit more. Again, it's hard to tell with something like that whether it improved us because it's actually an improvement or because because it just ran faster that time, right? We don't know specifically with our code. But again, I think that doing something, I think that probably there are two things that we can do that'll improve this. One would be using a 2D array rather than a map, because our map is going to be slow. And so, for example, if we can define what our relative position, we can define the range of our relative positions. We basically, what we end up having to do is we end up having to have an offset, which gets a little bit tricky, but we could hypothetically do it. The other possibility is that we can consider a bottom-up solution, right? So a bottom-up solution in this case would be, usually is going to go faster just because we're not using recursion. So let's think for a minute about how we might come up with a bottom-up solution to this problem. So with a bottom-up solution, we're basically going to initialize our array first, and then we are going to fill in the values in incremental order. And what I want to think about when I'm doing the bottom-up solution is I want to look at this recursive call and think about okay, well, how are we going to build from here? How are we going to take this and essentially work backwards? And so what could we do here? Well, one of the things that I noticed right off the bat is that we could probably be a lot more efficient with our space usage, because we're always looking at k-1 every time. And so we could do this in a way that would probably be a lot more space efficient. Let's actually start mapping out a solution. So in a case like this, what's our base case here, right? Our base case is when our relative position is 0 and when k is 0. So if k is 0, then we really want to start with k is equal to so if k is 0 and relative position is 0, then fine, right? Then otherwise we work backwards from there. So when k is equal to 1, then we're essentially building out from that end state, which allows us to so what would our array need to look like? I think the maximum range of the range of the relative position would have to go from, so let's say int relative position is equal to end position minus start position, and the total range basically has to go from negative well, really, we can't go I don't know. This is kind of like an annoying thing to implement. So that's just what I'm thinking. Like, if there's a cleaner way to do it, or for example, if there's other optimizations that we could make, because implementing this, I guess one thing that we could potentially do that. I guess we should probably draw this out, right? So let me jump back over to the iPad here. All right, so let's think about this for a second. Like, let's, if we have our number line here, and then we have our, let's say we have our start and our end. Start and end. And then let's say that k is equal to, let's say k is equal to some like big number, like 100. So hypothetically, we could go this way, a very long way, and then come back to get from the start position to the end position. Right? Like we can go a pretty long way in either direction. We can basically go, well, we could go, I guess like an absolute bound would be like we could go k distance in either direction, right? We can't probably really go k distance in either direction unless our values are k apart from each other. But we could basically go k distance in either direction. So the range of our relative position is basically negative to positive k. And then the range of k itself is obviously 0 to k. So if we go back to our to here, like we get our relative position, and then essentially our it's going to be like k times 2, and then I'm going to include the +1 to basically handle that midpoint, and then k plus 1. And so that is really our DP array. Now again, I don't actually think that we need to initialize this whole thing, because we can really just say, okay, well, for k is equal to, we can basically just do for each value of k. Right, so let's think about it this way then. So we'll initialize this. So essentially what I want to do is I want to start with k equals 0, right? And when k equals 0, there's exactly one valid path to that endpoint, which is that midpoint. So dp k times 2 is going to be equal to 1, right? It's the midpoint of this array. And now for the next step, I'm essentially just looking again, I'm looking at these like relative positions, right? So I'm going to iterate over this array, and I'm going to say for, and we can probably make this a little bit easier by saying for int j equals 1 and j is less than dp.length minus 1 j plus plus. My new value in, I'm going to initialize a new array. Is going to be equal to new int dp.length. New dp of j is going to be equal to dp j plus 1 and j minus 1, right? Oops. Plus 1 and minus 1, right? I'm pulling from here. So dp j plus 1 plus dp j minus 1. And then with these, we can do this same whole thing of we'll convert these to longs. So we'll basically do right, so it's basically that. And then when we repeat this, ultimately what we end up doing is we return dp, oh, and then we have to say, once we're done with this whole thing, dp equals new dp, and then dp relative, we're essentially returning dp relative position plus we have an offset, which is k times 2. We'll have to comment this out, right, for this to work. If we do something like this, all right, so we got line 42, we got out of bounds. Yeah, so this, I guess it should be plus k, right? And it's because it's k times 2 plus 1. And then that also means, did I do that right? Yeah, because this should be k as well. This k is going to be the midpoint since it's k times 2. All right, so that one worked. And let's see, I don't know which test case this was. Okay, so it passed, because I always wonder with these ones, it's like how many of the test cases did we pass? Right, did we fail the second test case or did we pass most of them? So let's see with this one what our, what was the issue? What was the one that failed? This, okay. So, and this is the start position is 1, the end position is. All right, so this is basically one of these examples where we're using exactly k steps and there's exactly 1. This is almost something that we could handle as like a special case too. Like we don't, because we had some of these, like with some of these things that we looked at before as well. It's like if these are both, I think these we could both just test right off the bat, might make more sense than, right? Because if the relative position is greater than k, then there's no way to do it. And if the relative position is exactly k, then there's only one way. And so, you know, this would solve this specific test case anyway. Should solve it correctly, right? Because we're just handling that case. When we look at this, okay, see, this is exponentially faster. And the only thing that we changed here, well, the two things that we changed here with this iteration of our solution. So let's go back to our code for a second. So the two things that we changed here are, one, we went from a recursive solution to a bottom-up solution, and two, we used an array instead of a map. And so I will say with this, this is one of those ones that I think can get really tricky to convert from this top down to bottom up, specifically because of the fact that we have to, our relative position can be negative, and we're trying to index on the relative position in our array. So essentially what we had to do here was we had to say that we have an array that basically goes from negative k to k, but that the 0 point is in the middle of the array, right? Because we can't have an index in our array of negative k. And so essentially what we do is we initialize this array that's like 2k, and then we shift the whole thing by k. So if we want to get the proper index, like we basically have to add k to our value, right? So if I wanted to get the index of negative k, I would do negative k plus k. That would give me my offset, and then the index would be 0 in the array. If I wanted to get the index of 0, I would do 0 plus k, and that would give me that index of k, which again we use here as that midpoint. So I know this can be a little bit tricky, and this definitely takes practice to get this right. As you can tell, like even with the practice that I have, it took me a while to kind of work this out, but the basic principle still applies, right? All I'm doing is I'm still just pulling this logic from here, and I'm saying, how do I convert this into this bottom-up solution? So that, honestly, for a to get an efficient solution and for a medium problem is actually a lot trickier than I expected it to be. So I'm curious if there's any like I'm curious if there is just like a mathematical solution. Can't really tell what's going on here, so I don't know. But because I wonder, there may be a way to calculate this more directly mathematically, but I think that this dynamic programming approach probably is the most realistic for most people at any rate. Whew. So that was exciting. Let's look at the next problem here. All right, so we're given an array nums consisting of positive integers. We call a subarray of nums nice if the bitwise AND of every pair of elements that are in different positions in the subarray equal to 0. All right, so return the length of the longest nice subarray. A subarray is a contiguous part of an array. Subarrays of length 1 are always considered nice. Okay, so in this case, the subarray 3, 8, 48 is nice. Basically what they're saying is that they share none of the same bit orders, right? So like if I have like 3 is gonna be 1, 1 in binary, and then 8 is going to be 1, 0, 0. So if you and the two together, right, we're going to get 1, 1 and 1, 0, 0. And so like, you know, if you line these up and you do a bitwise and, they all result in 0. So that is fine. I'm wondering with this, so obviously we could just look at all the different subarrays. It's not going to be that demanding for us to do the, like computationally demanding for us to do the bitwise ands. I'm wondering with this, is there a way that we could, for example, do like a sliding window or something? Is that, because that's my immediate thought when I see, you know, find the like longest subarray or something like that. It's like, could we do a sliding window And I think that we probably could, right? Like essentially what's going to happen is we're going to start with a subarray of length 1, and we're going to expand it to length 2, and we're going to see if it's nice or not. If it is nice, we keep expanding it until it's no longer nice. And once it's no longer nice, the only way that we can make it nice again is by shifting from the other end. So yeah, I don't see any reason not to just do, you know, a fairly basic sliding window here. I think that the and the nice thing about our and is that it is okay, so actually here's a challenge with that, is that when we compute our and, it's like, how do we then remove a number from, how do we like essentially un-and a number from our subarray? I'm not sure if there's a way that we can do this without then having to recompute for that whole subarray. Because it's like when we want to remove that first number from it, like when we and it with another number, we're potentially losing information. If we XORed, then we would be able to just recover it, right? Because if you XOR something with itself, it just gets zeroed out. With an and, that's not the case. I guess like one thing that we could do is, rather than and them at all, we could track like the number of essentially occurrences of bits in each index, because that way, rather than computing the ands at all, we would just look at the number of bits in each index compared to the total number of values that we're looking at, right? Because essentially the question is there any index where all the numbers in that range have a 1 in that index? Yeah, so like we could do, we would probably want to like implement some sort of helper to do this. So for example, so essentially what I'm going to do is I'm going to say is going to be, and then for just trying to think what the easiest way is to do this. I guess I could have like a we could just have like a mask, and then if it's essentially going to be if num and mask is greater than 0, bits I equals 1. And then we shift mask. So like if we do something like that, alright, so in this case, yeah, like this basically did what we wanted it to. I mean, it's in reverse order, but like as long as we're doing them all the same, it doesn't matter. So that's fine. Then, because with this, what I can do is then I can basically, again, keep like a running count. And so like what I want to do, what I have in mind for this is doing a sliding window, but I'm gonna keep a running count of the these, and then basically check that way. So how's this gonna work? It's gonna work like now we're basically gonna say for int, and actually we can just do it this way, right? So for end equals 1 and is less than nums.length and plus plus, we're essentially going to keep expanding out our binary array. So another, what I can also do here, so what I'm going to do is I'm going to pass in the binary array, and I'm going to pass in an int n, and I'm basically going to say for int I in binary array if I equals n, return true. This is just going to be my check. So it's like so essentially that way I can say while not has value of count binary array and minus start. What I'm going to do is I'm going to remove values, right? So I'm basically going to say binary nums start, And then for int I equals 0, I is less than start array dot length I plus plus. Binary array I minus equals start array I. Right, I'm basically going to remove that value. And then once I get to a point where it is valid, then I'm going to update my max length. I'm going to say max length equals math.max length and minus start. And then ultimately we're going to return max length. So doing something like this, I mean, I don't know that this is really going to help us that. It's like the advantage of this is that it is giving us, even though we're scanning over this array, this binary array every time, it is a fixed size. So at least that's going to be more efficient than if we were to scan over every subarray that we might see. Like in practice, I don't know. It kind of depends on the size of our input, whether this is actually going to improve our complexity or not. But let's see how this goes for us. Start array.length. Line 10. Oh, I think this is fine. All right. Okay, so I think we didn't increment our start. That would be a problem, right? So in here, start plus plus, and then this should actually be outside anyway. All right, so we did not get the right answer in this case. So let's see what happened. So I'm just gonna print. Let's start with this. All right, so am I doing this? I think I might be doing this backwards. I think that because we actually want it to be all 0, right? So while it really should be while it has value of count, right? Like what we actually want to be doing is if we have anything that is, hold on, let me review this again. Because if the and of every, okay, so I think I might be misreading this a little bit, because it should be that if it's the and of every pair of elements, that's different than anding all the elements, right? So the and of every pair of elements, that basically means that, and I mean, we can actually still do this using basically the same logic here. It just means that we really need every value to have a count of exactly 1, right? So rather than this can really just be if I is greater than 1, we want to return false. And then otherwise, we return true. And then what this is going to do is say, while anyone has value, has I'm not going to change the naming. I'll need this though. So if any of them has a count of greater than 1, we want to remove, right? So I think if we do this, that might actually solve our, or get closer to solving our issue anyway. So we're obviously not updating this properly. Oh right, because we're not adding the new ones in. That's the problem. Because the other thing that we could do is probably extract. So what we should do is first we should add in the new array, right? So what we should be doing is we should be saying I'm gonna go ahead and just initialize this to 1 because we're basically, I'm gonna say for, let's say, right, so this is what we really need to be doing first. And then we're removing here, and then that's gonna get us closer at any rate. So let's again see what we're getting here. So we get 1, and then 3. So 1, 4. We are ending up with I think this just needs to be n plus start, n minus start plus 1, but I might just be making that up. Or not. Okay, so let's see. All right, our approach is not very efficient here. I wonder, yeah, I mean, obviously this works, which is great. I'm just trying to think, like, what are some obvious areas for optimization here? I think that, um, I'd imagine that this, all this converting into these arrays and back is kind of killing us time wise. Um, like our solution obviously isn't a very good one compared to a lot of these solutions. I'm just trying to think what would be a maybe better way to tackle this. Like we could maybe use some sort of other someone said use the OR operator to create a mask of all valid elements of the window. Um, Not really sure what you mean by that. Yeah, like there might be other like bitwise things that we can do. I'm not too concerned about it. I think, principally, we have something that works here. I think that there's probably like bitwise operations that we could do to improve this. Um, but I'm happy with this for now. And I do have to run anyway because I'm late for another meeting. So, with that, I'll go ahead and wrap up. Thank you everyone for joining me as always. I appreciate you all and hope you have a nice rest of your week. And I'll be here next week. So have a good rest of your day.